All right, welcome viewers. Today we want to continue on what we did on design of retaining wall, and today we are going to look at the base reactive pressure. How do we design the base reactive, the base? How do we design the base of the retaining wall? Now let's look at several different load cases that we can encounter during the design of the base. Now remember that the pressure at the base, we call it Q. We have Q to equal to RV over B, open bracket 1 minus plus minus 6E over B. All right, remember the B represents the weight of the footing. All right, now we have the toe, we have the heels. Now when we carry out a design, we try to obtain the maximum and minimum pressure that can be exerted on the strip. We'll find out that there are different possibility of load cases that could be encountered. The first one is load case 1, where we have our Q, maximum pressure, and we have our Q, the minimum pressure. If you look at it, the minimum pressure Q is greater than 0 in this case. That is case 1. Alternatively, we can have a case where we have the minimum pressure Q minimum to be equal to 0, like we have in case 2. Where maximum pressure remains the same, but the minimum pressure becomes 0. You can see the distribution of the base reactive pressure under the base of the footing. Okay. Then the last we can also encounter is a situation whereby we have part of the base being subjected to pressure, while the other part is left empty, like we've seen in this diagram in case 3. Our Q maximum remains the same, but within this boundary here down to this point, we don't have any pressure. All right. So when we have a situation like we have in case 3, we can say that there's a loss of contact pressure within this zone, because here we're going to have negative value for our pressure. All right. And of course, we don't design with negative values, so we are going to design the footing using the positive pressure. All right. Like we earlier said in our previous video that in a situation like this, it will cause heavy tensile stress to be developed at the toe of the retaining wall. Similarly, also, we are going to look at under these various load cases, what are the range or domain of eccentricity that is expected to be obtained during design. All right, so if we have the minimum pressure to be greater than 0 and the maximum pressure as Q maximum, the eccentricity we are going to have is an eccentricity that must be lesser than B over 6. And likewise, when we have the minimum pressure to be equal to 0, we're going to have an eccentricity that is equal to B over 6. Okay, so but let's look at how we derive that. The allowable eccentricity that is needed to be able to obtain an effective and efficient base. All right. Now, if we look at case 2, you agree with me that this portion of the base is almost useless. You can see from here, there's no pressure. So what it means is that whatever design you are designing is for this region. Of course, in practical terms, you don't design, you have to design for the entire footing. Okay. So what it means invariably is that the whole of this section, which is where we have a loss of contact pressure, is as good as useless. It has no functionality, and as such kind of design where we have this kind of loading is a very uneconomical design. So we can say in this case 3 that this section, the base of this retaining wall is not efficient. All right, it's not efficient. Okay, let's look at the allowable eccentricity that is needed for the vertical load. The allowable eccentricity. So let's look at the allowable eccentricity. Now, if we look at the eccentricity, we say the allowable eccentricity for an effective base that is very efficient and functional is a situation of where we have the Q minimum to be either equal to 0, like we have in case 2, or greater than 0, like we have in case 1. Okay, so in doing that, what it means by that, it means for us to have an efficient base as footing, we should have a situation whereby our Q minimum, which we have on the board, uh, our Q minimum, which is RV over B. Remember, this formula we are considering a 1 meter strip, so we have B here times 1 meter, so we have RV over B. So when we work that out mathematically, let's take the first scenario where we have this RV to be equal to 0. We'll have eccentricity to be B over 6. And when we have RB to be greater than 0, we'll have eccentricity to be less than B over 6. Okay, now let's look at the base. Remember that the resultant, the center of gravity of the base is at this point, B over 2, B over 2 at this point. Now, it is expected that the eccentricity, for us to obtain an efficient base, our resultant vertical load must lie at an eccentricity that is either lesser than B over 6 or equal to B over 6. So if this is our 0 point, which represents our center of gravity of the base, it means that from the center to where the resultant load RV acts should be either equal to B over 6, or it can be anywhere within this domain. All right, that is when we consider that our resultant vertical load is acting on our left hand side of the center of gravity. On the other case, if we have the resultant vertical load acting on the right side of our center of gravity, the same applies. It means from 0 down to here will be B over 6, and whatever eccentricity you are going to have also should lie within this domain. All right, so invariably what we are saying is that whatever eccentricity that you're going to obtain in order to achieve an effective and functional base is a situation where you have your eccentricity within this domain. All right, and if you do that from here to here, we say the maximum is B over 6, here to here maximum is B over 6. So if we add them together like I've done on the board, here B over 6, here B over 6, if you add them together, you are going to have B over 3. Okay, so B over 3. So if here's B over 3, what's the leftover this way? We'll have B over 3 here, B over 3 here. Now you can see that this is a third of the base, and if it's a third of the base, the middle of a third of the base is this center within this point. So that is what we call the middle third rule. So the middle third rule is a rule in design of the base, either for a strip footing or a pad foundation, whereby your eccentricity must lie within that domain. Okay, so now we've done that of the eccentricity. So we are going to look at the third case, which is case 3. Now in case 3, we have lost pressure. Of course, for this same structure to still stand and remain stable under equilibrium, we are going to remember that we've lost some pressure, but for this structure to still remain standing, what it means is that the total load, resultant vertical load that is coming on the soil must be equal to the base reactive load that is going up under equilibrium. Okay, so if that is the case, because you can design like this, but it's not that you can design like this, but it's not going to give, it means the whole of this section is wasted, the concrete in this section is wasted, the steel reinforcing bars that are running down to this direction, they are all economic waste. But if you choose to go that way, it's okay. But if you must go that way, what it means is that you must find out what portion of this footing have contact pressure. You can see, let's call from here down to this point our C. So if from here down to here is our C, This is the portion that have contact pressure. The whole of this side have lost contact pressure from the soil. But let's find out the value, the distance to obtain the C. Now we know that for this load to remain at equilibrium, it means that we must have our sigma Fy to be 0, meaning that the total resultant vertical load RV that is coming, which is RV, let's call that one coming positive, must be equal to the total resultant load that is coming against it. Let's be equal to, sorry, positive. What it means is that RV must be equal to, so it means that this triangular load must act at the same point as the vertical load in order to maintain equilibrium. And of course, we know that triangular load acts at a distance 2/3 of the distance covered and 1/3. So what it means is if this is equal to this, we can say that if we decide to take a moment about any point, we know that from here we have the eccentricity. Let's draw it out. Let's say this is our center point. This is our resultant. This is E. Let's call here X, the moment arm of the resultant force. So if we do take moment about this point O, and this is our resultant force, which is RV, we are saying that RV times our moment arm will be equal to, for the triangular load, let's call the load, we've called that load to be Y. So I will know it will become Y times the centroidal distance from here to here is 1/3 of C. Okay, so if that is the case, it means we'll have our RV bar X equal to YC over 3. Remember that we said that RV must be equal to Y in order to maintain equilibrium. So what it means, this and this are the same, so they are going, so you have your bar X to be equal to C over 3. And it means that C becomes 3 times bar X. All right, so if that is what it means, C becomes 3 times bar X. All we just need to do is to look for the moment arm, and we can obtain our C. Okay, but recall that if we have that particular problem like this, let's say this is our center O, this is our RV, this is our E. From here down to where we take our moment is our bar S, which is our moment arm. So what it means is we'll have from here down to here to be V over 2, which is half of the base of the footing. What it means now is that bar S plus E is equals to B over 2, and it means that our moment arm becomes B over 2 minus eccentricity. Okay, so that is our moment arm. I will say that our moment arm is equal to, C over 3. So from there we can derive the expression for C. Okay, so if we do that, we should have our C to be equal to B over 2 minus E, or bracket 3. So this is the value for C in this problem. All right, so the next we are going to look at is how we can design the footing. All right, we'll look at the principle of designing of the footing and also of the stem. That since the minimum pressure is assumed to be 0 at point C, we are saying that the formula Q in terms of C will now be the same formula RV over C, plus or minus 6E over C. All right. The general formula remains the same since we now assume that at point C the pressure is 0. Okay. Now we also know that the minimum pressure will be equal to 0 at point C, and if we do that, we'll have the eccentricity at that point C to be equal to C over B, C over 6. All right. So we have C over 6 at that point. If you observe, you will discover that that same eccentricity formula for eccentricity is the same as the one we have in case 2. Okay, in case 2 we have B, we have B over 6. So but in this case now we're having it as C, so we know what our C stands for already, so we can obtain C. Now if we go with that, it means also that the maximum pressure at the base, substitute the value of eccentricity into the maximum pressure, we'll have that maximum pressure to be 2 RV over C. Okay. Now, if you look at it, it's also applicable, like I said, it's applicable to case 2. The only difference between both is the C and B, where C represents the entire width of the footing, where we have B to represent the entire width of the footing, we have C to represent part of the footing. Okay. Now, we say that the maximum pressure when it is B remains the same formula as the maximum pressure when it is partially in contact with the footing. Now this means that the general formula for the maximum pressure remains the same irrespective of either case, whether case 1, whether case 2 or case 3, whichever case your design fall into the process, the general formula still remains the same. All right. So the next we are going to look at is the design of the base. Talking about the design of the base, we're going to look how to generate the moment and the shear for the heel of the retaining wall and as well as the toe. We are going to idealize the retaining wall. I break it this way, like a cantilever we have here. This portion we're going to have the stem. On this portion we're going to have the toe. Okay, so we already know the pressure that are acting. Let's assume we have a case 1 scenario where we have let's call this one first our toe. Let's call this one our heel, and let's call this our stem. All right. So the distribution of pressure, let's take for example a case 1. I'm just going to derive the general formula so that you can find it easy to carry out your design whenever you are using numeric values to do your design. Okay, so now let's look at this. The pressure distribution goes this way. This is the base. Let's take case 1 for instance. We'll have the pressure distribution like this. All right. Sorry for the drawings. Okay, so we'll have this one as the base. So we want to obtain the moment expression and the shear force expression. Okay, now if we break this at the middle, the first thing we need to know is that we have here as our Q maximum. Here becomes our Q minimum. Okay, now we need to obtain for the cantilever side, let's assume we break this side, let's assume we break them into 2 portions. Why this portion is for this other portion remains for the heel. We have the other one for the toe. Now the first thing we would like to do is to take an expression. Okay, because when you look at the linear variation of the load, you discover that we are going to obtain the slope. Okay, we are going to obtain the slope. Now, in obtaining the slope, we are going to express it in terms of x. Let's consider the toe, which is this portion first, and let's obtain the load function as well as the shear force and bending moment expression. We'll obtain that of also for the heel, and as well uh, obtain uh, that for the stem. So considering the heels for our design like we've done, we splitted the toe and the heel. Now, if we consider the heel, the cantilever end is the zero end at this point. So we're going to take it to this direction. So we are taking an expression in terms of x, the distance in terms of x from 0 down to b1. So if we do that, we are going to have our slope, which remember from the general pressure diagram, we've already gotten the slope as Q maximum minus Q minimum over B. Okay, and that is a positive slope. Also, by the time we split the beam like we did before now, we have this as our heel, and we have a load on top of our heel, which we call Q1, and that load comprises of the load due to self-weight of the heel plus the surcharge load that is acting on top of it, plus the self-weight of the soil acting on top of the heel. All right. So when we do that, we'll have the total load for Q1. Now we know that is the straight line, so we go by the equation of the straight line, which is y is equal to ms plus c. Now remember, these are 0 point. We are moving down this way. When x is 0, we have our intercept to be q maximum, to be q minimum, sorry, from the initial diagram we drew. So we know that our intercept at this point here is c, okay, which is a q minimum. All right. So if we write the load expression as a function of x, we'll have a qx, we'll have the slope, we'll have our q minimum minus the load coming in the opposite direction, which represents our surcharge self-weight and as well as the self-weight of soil and that of the heel. Okay. So if we integrate that, we'll have that the shear force expression becomes s squared s x squared over 2 plus q minimum x minus q1 x plus a constant of integration. All right, if we take the constant of integration, we know that that is 0. So we can integrate further to have our moment expression. So if we work on this moment expression by integrating that of the shear force expression, we are going to have this as a moment expression. X raised to power 3 x raised to power 3 over 6 plus q minimum s squared over 2 minus q1 x squared over 2. All right. So this gives us the moment expression for this particular heel. Okay. Now let's look at that of the toe. If we consider the toe is on this side, so we're starting from the 0 point here. We're moving down to this direction. Remember that the slope we took initially was when we were coming to our left hand side, but now we're moving to our right hand side. So here becomes the origin. So when x is 0, here is a q maximum. So that becomes our intercept. Okay. Now our slope is moving this way because when you minus the minimum from the maximum, you have a negative value. So we're going to have our mx, which represent xs, to be negative. All right. So what we are saying is that the load function qx is equal to q maximum minus xs. Then we have minus our self-weight of soil on the passive zone. Okay. And as well as that of uh, the toe. Now let's go on, write this expression as we look at it. All right. So when we write it, we have it this way. Remember, so our Q2, we say self-weight of the toe plus self-weight of the passive soil. All right. Now the next we're gonna do the load function with this is the load function. with a function of x. Then we'll have, by integration, we have this the shear force expression and the moment expression as well. Okay. Now let's quickly look at the reinforcement and the mode of failure of the retaining wall. Okay. Now, when we look at the retaining wall, what we have here, we know that for this wall to fail, there's going to be lateral pressure from this direction, which will cause a bending effect on the stem. Okay, so when this causes a bending effect on the stem, we can as well have the stem. You can see that while it's bending down, it's pushing down the toe, causing this place to be under compression, while the bottom is under tension. Similarly, if you look at the heel, you discover that why there's a lateral force acting in that direction, there's also a vertical force trying to withstand the bending effect of this particular heel. So if you look at it, you see that at the top surface of your heel, you have a compressive, you have a tensile stresses developed at the top, while at the bottom of the heel slab, you have a compressive forces. Okay, so what it means by our design is for the stem, we are going to have the zone where we have the active soil to be the tensile zone, to be the zone that is under tension. So our design of that stem is to take care of the tension zone, and while the other side of it will be under compression. So that's why we say, if you look at the detailing here, the main bar that we're going to design for is the main bar, which is this, all right, which is this. We can put a distribution bar, this distribution. Then we have that as our detailing. Okay. Now, in order to take care of cracks, you can decide to put nominal reinforcement on this other face of the wall, and as well distribution bars to take care of it also. All right. Now let's look at the heel. Now, when we look at the heel, we are going to see that, like I described here, the top of the heel slab is going to be under tension. So the main reinforcement for this heel here is this, okay, is this bar. So you are going to reinforce it as a main reinforcement, why this becomes the distribution bar. All right. Also, if you look at the toe, if you walk on the toe, remember the toe comes this way to the left, while the toe, you are going to have the main reinforcement will be at the bottom, and you're going to have distribution bar. Now you can as well extend this reinforcement for the heel down as the top reinforcement for the toe. All right, so we can also extend that of the toe, the reinforcement, the main reinforcement for the toe bottom. We can extend it down to that the direction of the heels. All right, so we can have that. Okay. Now, also take note, to obtain the pressure, the moment due to the stem, all you need to do is to integrate the function of the stem, all right? Integrate the pressure function of the stem. Once you integrate that for shear and also for moment, you have the moment expression, all right? So this brings us to the end of the lecture. If you are new to this channel, please do wait to hit the subscribe button and also like the section. I remain your host, Engineer Baga. I will see you in our next class. Have a wonderful time. Stay cool.